All right, I think let's get started. Hope everyone can hear me very well. Uh, Good morning, good afternoon, or good evening, perspective to where are you? Thank you for joining us for this webinar organized by the Canadian Geotechnical Society and Professional Committee. My name is Rajit Ayaran. I am a geotechnical engineer at WSP based in St. John's, Newfoundland, and I am serving the CGSYP committee as the knowledge lead and will moderate today's webinar. The CGSYP committee, initiated this webinar series to allow young professionals to enhance their knowledge in a range of areas of geotechnical engineering. We have successfully conducted 8 webinars so far this year. So today is our ninth webinar. So if you are interested in listening to our past talkings, recordings are available on our YouTube channel, and I will post the link in the chat. Before we get started, there are few housekeeping notes. As you notice, to avoid any disturbance, I disable audio and video access. So if you have any questions, please use the chat option. The webinar is recorded and it will be available later on our YouTube channel. The presentation will take 40 to 45 minutes and there will be a brief Q&A session at the end. So if you have any questions for the speaker, please type them in the chat and I will take them as they appear. So today it's my great pleasure to introduce our speaker, Dr. Marc Smith. Marc, my workmate and is also a mentor to me, is a principal geotechnical engineer with 38 years of experience in dam safety and geotechnical engineering. He joined WSP Canada Hydro and Dams Division in 2019 after working for Hydro-Quebec. He was involved in the design and construction of numerous large embankment dams, as well as surveillance and monitoring of structures during the impoundment and operation phases. He carried out various specialized dam safety analysis in Canada, as well as in Latin America, Africa, and Asia. He conducted many geotechnical research projects with Hydro-Quebec's Research Institute and the Industrial Research Chair on Embankment Dams of University Laval, where he is, currently serving as an associate professor. He's also a lecturer at the Polytechnique de Montreal for graduate courses on dam engineering. He's a board member of Canadian Dam Association and chairs its international committee. He acted as a Canadian representative in the European Working Group of Internal Erosion, which led to the publication of Bulletin 164, Internal Erosion of the Internal Commission of Large Dams. He was also involved in the Risk Technical Committee of the International Society for Soil Mechanics and Geotechnical Engineering. He authored more than 40 technical papers in peer-reviewed journals and publications. He participated in many activities for the promotion of scientific careers and is actively involved in his community. Marc has won awards recognizing the excellence of his research and his community work. So we have an experienced engineer and researcher with us today. Without further ado, I would like to invite Marc to deliver his talk on internal erosion and seepage detection in embankment dams. Over to you, Marc.
Thank you, Regis. So hearing me well? No problem.
Yeah. Yes, I can. Yeah.
Perfect. Okay, so thank you, Regis, for this kind introduction. And also thank you for the Canadian Geotechnical Society Young Professionals Committee for inviting me today to talk about internal erosion and seepage detection in embankment dams. So you will see the context of my presentation is directed towards hydro dams, but just keep in mind that all these concepts can readily be applied to mining dams as well. So internal erosion, or IE, in this presentation. We see an example of that here on an embankment dam, a test site, basically. Just to put a bit more context into that, there is a lot of academic research going on for internal erosion. So this is a very hot topic in terms of academics, but also it's prevalent everywhere in embankment dam safety practice. So here there's a test site where we see seepage coming out of the embankment. So the seepage comes out, increases in flow, but carries with it the finer particles of this embankment, as we see here, as seepage progresses. And ultimately, this leads to a breach. So basically, internal erosion is what it is. In fact, erosion of the soil internally due to seepage forces. And as we can see in the photos, this is a process. So it's not an instantaneous occurrence. Uh, Internal erosion is one of the main, in fact, the main geotechnical cause of dam failures in the world, as we can see here. So there's an example, another example of internal erosion going on. So we see the reservoir and we see lots of seepage coming out of the dam, as well as the dam being eroded. Another let's say, prevalent cause of dam failures is what we call external erosion. The reservoir overtops the dam, as we can see here. But the primary causes of this are more related to hydraulics, hydrology. So basically, in geotechnical engineering, internal erosion is the main issue in terms of the dam design, construction, and operation. As I said, there is lots of research going on in this field, including this group here, which is still quite active into bringing together practitioners and academics to, let's say, increase the knowledge about internal erosion. For more info, the website is here. Also, academic research and also practitioners are very interested on this subject. For example, there is one bulletin here that was published by the International Committee on Large Dams. In fact, it's a fold bulletin, volume 1, volume 2, in which all the, let's say, concepts behind internal erosions are explained, and volume 2 is mostly examples of internal erosion. So my presentation is basically based on the concepts presented here. And also just to mention to everyone that these bulletins are available almost free of charge. So one way to do so is to become a member of the Canadian Dam Association. You can be an individual member, or if the case applies, you can be a student member of the CDA and have access to this bulletin and all the other bulletins. Just to mention that the student membership is $5 a year. So the general process of IE is basically shown here. So we have an embankment, we have a reservoir, and no water downstream. So we have delta H, we have a hydraulic load on the dam. And depending on the dam characteristics, the seepage forces, etc., this seepage through the dam can erode internally its particles. So as seen in the previous photos, this is a process that could take a somewhat long time, relatively long time to start, but when it starts, it accelerates and can lead to a breach. So the initiating mechanisms of that involve soil particle under seepage with sufficient energy. So the particle are driven by this energy, which is the hydraulic load here. So for internal erosion to occur, there must be seepage, obviously. Also, presence of erodible material along the flow path, and also a possibility for this eroded material to escape out of the dam. So these three conditions that must be met if internal erosion is to occur. So corollary, these three should not be met we should prevent it as dam designers. So we must prevent the presence of erodible material and also the possibility for it to escape. So internal erosion always implies the presence of seepage, but the rivers is not true. Seepage does not always imply the presence of internal erosion. So this is why it's so difficult to detect it in the field. So internal erosion, it's not completely a 0-1 event. It's not on or off. There are contributing factors that make the likelihood of internal erosion more or less likely. So one of these contributing factors that, let's say, increase the likelihood of internal erosion is unfiltered exit and unfiltered seepage exits. So here we see let's say, flow net of an homogeneous dam on a homogeneous foundation without any filters, without anything. So we see the seepage exits here, which are not filtered. So I'll talk a bit more later on filters. So the seepage can come out freely, as well as the particles that are eroded. So here we see that same dam with more vegetation where the seepage exits, and also here the particles that are eroded out of the seepage. Another contributing factor would be gaps or cracks in the dam, as shown here conceptually. So this is a dam core here, seepage flow net as well. So the driving force behind internal erosion is the hydraulic gradient. So basically the hydraulic gradient is equal to the head loss divided by the length of seepage. So it's a unit head loss. So here, at this point here, the hydraulic gradient is equal to delta H divided by the seepage length. If there is a crack or a more pervious layer, then this will obviously affect this, the flow net. And in this case here, the delta H remains about the same, but it's the seepage length that decreases. So by decreasing, this increases the hydraulic gradient, so it makes this system much more prone to internal erosion. Also, the seepage can affect the likelihood of internal erosion. As we have seen earlier on this seepage flow net, the soil and the foundation are homogeneous, are isotropic in terms of permeability. So the phreatic surface comes out at this elevation with gradient I1. If, for example, we increase the horizontal permeability by 20, so the material becomes anisotropic. So this is seen quite often in the field. So this makes the phreatic surface exit at a much higher elevation and also increases the hydraulic gradient. So anisotropy can increase the likelihood of internal erosion. And internal erosion can occur along many paths. So here it's the basic form of internal erosion through the embankment itself. Also, internal erosion is much more likely where at embankment structure contacts, such as the contact between a rigid concrete spillway and a compressible embankment dam, such as this one. So by settling, the dam can create gaps between the embankment and the spillway, and this flow path here is increases the chances, the likelihood of internal erosion. Also, the presence of conduits in embankment dams can also be a weak spot if not designed carefully. So as we see here, erosion occurred outside of the conduit, the concrete conduit. So here we see another figure showing that the conduit here and water coming out of it. So if, for example, if there's a hole in the conduit, then the seepage in the dam itself can go inside the conduit through this hole and erode particles with it. On the reverse, if there's a hole in the pipe and water flowing into it, then this water can come out of the pipe and erode the adjacent soil. So this photo here is an example of this having occurred. Also, the internal erosion path can go into the foundation or through the dam and its foundation. So basically, dam foundations can be quite heterogeneous, as we can see here. So the seepage path can take, the seepage can take any path it wants. And depending on the compatibility between the soil layers, then we can consider that the seepage is filtered or not filtered. So for example, here it's not filtered, so danger for internal erosion. It's not filtered here as well, so there's a danger here, etc. So we'll see examples of this later. And also one thing that is quite difficult when you go to inspect a dam, you see some seepage, such as this seepage spot here. You see material flowing out of the seepage. So is there internal erosion or not? So it's an easy question, but it's not an easy answer to provide. Because what's more dangerous here is not necessarily that we see soil particles moving. What's more dangerous is when we see soil particles accumulating out of the seepage. So if there is a continuous inflow of new soil particles that accumulate, then we can raise the yellow flag or red flag and say that most probably internal erosion is occurring. So in this case here, the water remains clear. It's only in the same soil particles that are moving but staying in place without new inflow of soil particles. So in this case, although it's quite spectacular, there is no internal erosion. So this is what is shown here on this figure. So no problem, possible problem, it's seepage flow carrying no material or no new material. And here there is a big problem where new material accumulates at the seepage exit. So what's difficult also with internal erosion is that there is no factors of safety really related to this phenomenon. So we can see here and there that there are critical hydraulic gradients and etc. But these concepts are more based on laboratory conditions and they are very difficult to apply in practice. So I wouldn't rely on any factor of safety estimation to provide me for an assessment of the likelihood of internal erosion. Also, internal erosion, i.e. occurs exactly at the areas where the conditions are most penalizing. So if we have a 1 kilometer long dam and there's one specific 10 centimeter wide area where the conditions for IE are met, then problems will occur there, regardless of the condition of the dam elsewhere. So it's really at the most penalizing area. And for slope stability, it's a bit different. The factor of safety for sliding is basically depends on the mean properties of the soil along the slip surface. So IE occurs as a process, as shown. So the first process is called initiation, where the soil grains begin to move. Continuation refers to the moving soil grains getting out of the dam system. So there is no filter. So initiation, particles begin to move. Continuation, the particles go out of the dam system. Progression means that there is nothing to stop the process. So by nothing, so let's say to stop the process, we can lower the reservoir, the dam can collapse in itself. So there could be self-healing, etc. So there could be phenomena occurring during continuation that stop the progression. And if nothing stops the progression, then the breach will occur. So 4 basic steps in the IE process. Here we see photos of the process occurring. So again, this is another test site in the Netherlands, the Eekdijk test site. So this is let's say an artificial dam, and that was heavily monitored. So all these flags here and wires, it was heavily monitored to, let's say, try to detect, to measure parameters that could help understand the IE process in action. So these photos are taken at the downstream toe of the dam, downstream area where seepage was made to exit. So at the beginning of the process, so let's say initiation, you can see that water is not clear anymore. It starts
Hello, Mark. I think we lost you.
Yes, I'm
Yeah,
still here.
yeah. Now it's working fine. Yeah, we lost you before.
It's okay? Yeah.
Yeah. Now it's working fine. Yeah.
Yes, I saw that.
Yeah.
Perfect. So I was in the process of initiating internal erosion at that Eekdijk test site. So yes, the water is cloudy here. So the first particles were starting to move. After a while, we could see some specific seepage areas where the particle content became a bit higher. After a while, then the specific area began to carrying out a larger amount of particles. And then after that, a hole could be seen and a delta made from these eroded particles could be seen as well. Then the delta became larger and larger again, and the hole wider. And all of this led to the rapid formation of a breach. So it's really a process that, going back here, that starts slow, but when it evolves to a certain point, there's pretty much nothing we do to stop it. An example of internal erosion is for the Teton Dam in Idaho that failed in 1976. Here we see the area before dam construction, after construction. On June 3rd, there was some seepage here. A few days after, the seepage was a cascade of eroded soil, which led to erosion shortly after. So this was filmed by a video camera at the time. So the initiation took place in the foundation of the dam. So we see the cross section of the dam. Zone 1 is the core, founded on rock. So the flow took place in the upper area of the rock, the bedrock, that was cracked, that was not treated in this area. So it started from there and eroded quite rapidly, but eroded in the key trench area in the foundation. So this is how it looks like right now. So the breach that was formed is here. So what are the main conclusions of this? So there were many factors that contributed to increase the likelihood of internal erosion. One of them was the fact they used for the zone 1 core an erodible soil, and the shape of the key in the bedrock. The shape was such that the hydraulic gradient across the key in zone
Mark, we lost you again. Can you hear us?
Yes, I'm
Okay,
back
yeah,
again.
yeah, you're back again.
Yeah, okay. So, and also there were no foundation filters between the, something's wrong here, between the key and the rock, the bedrock. So there were no filters. So the shape of the key trench, the compaction of the key trench, so all of this contributed to have material and hydraulic conditions prone to internal erosion. So basically, this shows here that all the latent conditions, as we see here, so all the latent conditions that we see here were in effect all at once. So it's like the Swiss cheese comparison. So if all the holes are aligned, then there is a likelihood of having a problem. So this is what occurred at Teton Dam. So the problem with the Teton Dam is that there were with a single line of defense instead of using belts and suspenders, which include impermeabilization, filtration, and drainage. So clearly filtration here was an issue. Also, there were human factors in this case study. So basically, the people there knew how to build an adequate dam. So it was not ignorance from their part. It was not absence of technology, because this type of dam was already built before. It's mostly for, let's say, political and administrative reasons. They preferred to reject some of the geotechnical concepts that could have helped in preventing the internal erosion failure. So this is not my judgment. It's described in this publication here, which is very interesting. So I suggest you to go and read it. This Mr. Sowers here analyzed about 500 civil engineering failures and came up with the conclusion that rejection of technology was the most prevalent cause of failure, such as Teton Dam. So back to the so the initiation phase, the first phase, can occur by 4 different mechanisms. So the first one is suffusion. As we can see here, so in the blue, these are the coarse-grained particles, coarse particles. In brown here, the fine-grained particles. And these blue arrows are seepage flow. So in this case, the soil as a whole is gap graded. So there are coarse particles and fine particles, so no medium particles. When that occurs and when it's subject to seepage, then the finer particles can erode through the coarse particles, so washing out the material basically. So this is suffusion. Also, you can have contact erosion. So at the interface between a coarse soil and a fine soil, so the seepage flow erodes from, as we can see here, erodes the finer particles out of the dam. Here we have the third mechanism, which is backward piping erosion. So this is the classical piping internal erosion mechanism. So when the hydraulic gradient is high enough and when the seepage conditions are detrimental enough, then the first particle comes out, the second one, the 1001, and the pipe here progresses towards upstream, leading to a breach. And finally, we have concentrated leak erosion, in which we have a crack here, for example, and the seepage flow erodes both sides of the crack in that example. So these four mechanisms are the initiation mechanism, the initiation phase. And initiation can occur more likely where there are discontinuities in the dam. So we have seen that at the contact of a rigid structure, such as a spillway, a conduit. So these are always weak spots for initiation of IE. Also, the discontinuities in the foundation can be detrimental. So if we have differential settlements, such as between here and here, cracks can occur and could, let's say, lead to, for example, concentrated leak erosion. Cracks can also occur if we have stress transfers between the dam and the foundation, such as here. So these are weak spots again for IE to occur. Also, when we assess the risks of internal erosion, we must assess basically at the same time the material susceptibility to IE, the hydraulic loads in our system, and also the stress conditions in our system. So it's not always an easy task. We have many things to consider at once to have a complete, let's say, picture of the internal erosion risks. Now, the second phase of the process is the continuation phase. And the most efficient way to stop this phase is to have, let's say, well-designed filters. So I was talking earlier a lot about filters. So here we see one, a filter. So on top, we have the material that needs to be filtered. So where the seepage is occurring, so basically the impervious core of a dam. Here we see a crack, for example, in which concentrated leak erosion is occurring. And down here, lower half of this figure, we see a filter. So material, fine material that needs to be filtered, and coarser material that constitutes the filter. So the two basic properties of filter are first to retain the eroded finer particles, such as seen here. And the second role of the filter is to drain, so to let the water out. So the filter needs to be coarse enough to let the water out, but fine enough to keep the fine eroded particles in. So coarse enough, but not too much. So again, we see another representation of a filter, a base that needs to be filtered. Seepage is occurring. Some finer particles were eroded, but they were trapped into the filter and water could easily go out. Here we see a typical cross-section of an embankment dam. In the zone 1 material, in this case, is impervious, semi-impervious fill, and this yellow material here is a filter. It's filter material. So basically here, this area is to filter seepage that comes out the central portion of the dam. This bit of an area here filters the seepage coming out of the core that could have go into the foundation. So that was missing for Teton Dam. And here we see other filter layers that could filter seepage from the foundation. Here we see a photo of a filter being built. So this is typically sand here. And on the other side, we see a dam core being built. In this case, it's silty sand. There are criteria to design filters. This one is well known. It's a Terzaghi, or it was named after Terzaghi. So it's the Terzaghi criteria, in which we have grain size distribution of the base and grain size distribution of the filter. So the retention criteria, so to retain the small particles, is shown here in blue. The permeability criteria, where we want water to come out of the system, is shown here in red. So this is the basic criteria. We have more, let's say, complete, more up-to-date criteria for internal erosion. One set of criteria that I like the most, in fact, is from this publication here. You can access to it from this site. So it's broadly based on this, but has many other components to it. So it makes it very, let's say, complete. So Teton Dam failure, in hindsight, what could have been done? So basically to have a wider excavation in the bedrock, to have a filter zone at the contact of the core and the bedrock, and also to better compact the soil of the dam core and increase its plasticity. So these are all options that could have been put in place and that could have reduced dramatically the likelihood of internal erosion. So it could have filled a few of these holes here and make internal erosion much less likely. So now, the other part of the presentation, seepage detection. So basically, we want to detect seepage because we have some kind of fear of internal erosion going on. So seepage detection and internal erosion are linked this way. So there's an internal erosion risk, which is controlled by the presence or not of filters, hydraulic gradients, and this is controlled by the presence of seepage, and seepage detection is to detect seepage. So again, internal erosion is always in presence of seepage, but seepage is not always a sign of internal erosion. So why detect it? So basically, it's one component of assessing IE risks to better understand what's going on and also to optimize possible rehabilitations. So before trying to detect seepage with the sophisticated techniques, visual inspections is always the preferred means for seepage detection. So visual inspections can be readily be done when the area to be inspected is cleared of vegetation, is readily accessible. We can see clearly seepage as shown here. We can monitor it, etc. So these are ideal conditions. Less than ideal conditions are shown here, where the downstream portion of the dam is covered by water. Also here, this water can freeze, so it's almost impossible during winter, let's say, to monitor seepage, in this case, beneath the lake that was there. We can see some warmer spots here that melt the ice, so we can assume that there is seepage going on, but it's difficult to monitor. Other typical, let's say, difficult situations for visual inspections is the fact that sometimes the area to be inspected is heavily vegetated, so it's difficult to see seepage. And another sign here is for here in the province of Quebec, we have lots of beaver dams, so these can affect our capacity to detect visually seepage. Seepage detection also occurs for concrete dams. So in fact, this is a masonry dam shown here. It's difficult to access the downstream face of that dam because it's so high and so steep, but still these little guys here can access it. So these mountain goats are basically, let's say, trying to detect seepage through the mortar of the masonry. So they can do it, but obviously we cannot. So not as easily as they do. So other ways to detect seepage in these situations is to use specific seepage detection methods. So seepage detection is here. We want to detect seepage and to finally assess the risk of IE. But what is shown here is that seepage detection is not an end in itself. We have also we need to also consider the monitoring data, the variability, uncertainties, all the geotechnical aspects. So these elements are typically the more important and also the more time-consuming in identifying potential internal erosion problems. So I'm talking about seepage detection, but bear in mind that the engineer has to do his homework before and after seepage detection. There are many types of seepage detection methods, so we need to define this. So what's the purpose of our seepage detection investigation program? So to determine the type of detection, we need to, let's say, define all these things, geotechnical related context, analysis, etc., to determine the type of detection we want and to choose in the seepage detection toolbox what we need to use. Also, the assumption, which is appear obvious, but it's not always that obvious. So seepage detection is a good way to assess internal erosion risks, but you need to do it in the early phase of internal erosion, like initiation, for example. So if the dam is near to a breach, then it's pretty much useless. So there are many ways to detect seepage. I'll talk about this method here, which is temperature measurements, the passive method. So heat transfer in soils is shown here. So as you know, temperature amplitudes in soil decrease exponentially as we go deeper. This is the same for a dam. So this mechanism here, this heat transfer mechanism, is called conduction. Conduction also occurs in a dam, but also we have convection, so movement from caused by differences in the air temperatures, and also advection, where the heat of the reservoir is transferred into the dam. So this is basically advection that we want to monitor to detect seepage. So in this method, we want to track the temperatures inside the dam and try to find areas where advection is occurring. So heat transfer in soil. So if we see the temperature, annual temperature amplitude, and on the y-axis, the depth under the crest. So the theoretical, let's say, variation in the temperature amplitude is shown here, and there is one here shown for a dam. So a dam is, the temperature amplitudes in the dam vary sort of this black line here. So that being said, if we have a dam that has low seepage velocity, the temperature amplitudes at the center lines will look this way. So basically the same as that black line here. Temperature at point B will vary during a year, such as this. So the temperature amplitude are very low. Temperature in the reservoir water will vary this way during a year. So the amplitude is much higher due to seasonal changes, etc. So this occurs when there is low seepage velocity and the heat transfer by conduction dominates. When there's a pervious layer in the dam, then the temperature amplitude along this axis here is shown here. So the dotted lines are, as we have seen before, where seepage is not that high, but here we have a much different temperature amplitude profile. So there's clearly a big difference here between the measured amplitude in this case and the measured amplitudes where conduction dominates, where seepage is low. So if we look at that based on time, the temperatures at point A in the reservoir vary this way, but the temperatures in the dam itself at point B are much more similar to the variations in the reservoir. So that means that the heat in the reservoir is transferred in the dam. So we have detected seepage that way. So this was done in an actual dam. Details are shown in that publication here. So thermistor strings were installed at the upper portion of this almost 100-meter high dam to measure temperatures in the reservoir, in the filters, and in the core of the dam. Here are the results. So this is the theoretical conduction only temperature variations, and this is the actual measurements, temperature profiles. So at elevation 355, there is clearly a more pervious zone that was detected. All these results are shown here, where we can see the annual temperature amplitudes, the distribution of these amplitudes in the dam core itself. So we can see the areas where they're more reddish color. So this is where the temperature amplitude is greater, so where the advection effect is maximum. So there is clearly here a preferential seepage path. So the million-dollar question is, why is there a seepage path here? And the $2 million question is it dangerous? So this is where all the geotechnical analysis and context come into place. So basically here, the permeability, the hydraulic conductivity of the in-place material was studied, was estimated. And if we overlap the hydraulic conductivity that was estimated with the temperature profiles, we can see that this maximum advection line was caused by the normal variations of permeability during the construction of this dam. So The variations were due to construction procedures. The behavior of the dam is okay, but still these variations can produce some preferential seepage path. So it was detected, and the presence of this zone is due to construction variations in material properties, normal ones during construction. So this is the $1 million question, why? And the $2 million question is it something to be afraid of? So here it is not, because the core material is stable, so very likely no initiation of IE. And also the seepage exits are protected by design filters, so there is no continuation. So all of this geotechnical work is basically related to this here. So again, it's the more time-consuming but important aspect of internal erosion assessment. So seepage detection, again, is just one component of the entire problem. So general conclusions, again, internal erosion implies the presence of seepage, but seepage does not always imply the presence of internal erosion. Also, seepage detection is to detect seepage, not internal erosion. So these are the key takeaways for you to remember, and also to remember that IE is quite a complicated phenomena, and also that there are lots of seepage detection methods, so you have a bit of homework to do before choosing one of these methods, and ultimately to assess internal erosion risks. So thank you for your attention.